Okay, all of our calculations we're doing in this chapter up to this point has been leading all the way to this point right here where we're going to calculate acid-base calculations of neutralizations. Okay, now that could be done in the form of a titration curve where you're figuring out the pH along the entire titration of that of those species, or it could be just as of a mixture where you're trying to figure out the pH of just two solutions of a certain volume and molarity and calculating the pH at that point, which is mostly what we're going to do here. Is we're going to worry about particular points and what is the pH. We're not going to actually derive a titration curve, but I do want to discuss that a little bit and show you what a titration curve is. Let's look at first a case of a monoprotic species, HCl and sodium hydroxide. It's going to form sodium chloride and water. And basically we could do a titration curve where we would take HCl would be our analyte, that would be in our flask, and we put sodium hydroxide in the burette, which would be our titrant, and we basically would go ahead and make a titration. We add certain number of milliliters of sodium hydroxide to the HCl, measure the pH. If we do that, we can get a titration curve, which is your pH on your y-axis, and your milliliters of your titrant, which in this case I'm saying sodium hydroxide. Okay, we'll measure the pH. If I add a milliliters or so, I'll get a measurement, then measure another one and another one, and just keep measuring as I add volume. And then what's going to happen is over time, it's going to get a steep little change, and then it's going to level off again. Okay, this area where it's doing that steep change, that's your equivalence point. Okay, that's the point where the number of moles of your reactants have been neutralized stoichiometry-wise. So in other words, we're saying I have no HCl and no sodium hydroxide left. I'm at that equivalence point, which is going to happen right in the middle of that steep slope. Now, since this is a strong acid and a strong base, it's going to be at a particular pH where that equivalence point is going to occur. Now, where will that happen? Well, let's look at what's forming as a product. We have sodium chloride. Well, what is sodium chloride? That is a soluble salt. What kind of salt is soluble salt? That's a neutral salt. So, since the only thing that's left is a neutral salt and water, that equivalence point is going to be at 7 pH. Okay, it's going to be at 7 pH. Now, is that going to happen every time we have an acid and base titration? The answer is no. That's going to happen when I have a strong acid and a strong base, because what's going to happen when I do that, I'm going to form a neutral salt. And we'll talk more about this later on, where I'll show you how to look and see where the equivalent point should be between an acid and a base. Now, this is for a monoprotic species. This same thing can happen with a diprotic. Let's say, for instance, carbonic acid and sodium hydroxide. Okay, that's basically got two protons being neutralized. Now, this is how we write it molecularly. H2CO3 plus 2 sodium hydroxides gives me 2 waters and sodium carbonate, but that's not how it happens in nature. It's going to do it one proton at a time. As I told you, for polyprotic stuff, we do one proton at a time as a calculation because it's happening one proton at a time. First, there's the first step. What's going to happen is I'm going to lose one proton. Okay, so I'm going to go from carbonic acid to plus sodium hydroxide to form water and sodium bicarbonate. Well, we're going to have that on a titration curve. I have my pH, and I have my milliliters of titrant, which in this case I'll say sodium hydroxide. Okay, that's going to have a small slope of change in pH, and then it's going to eventually slope up. Okay, where that slope up occurs is where that first proton is being neutralized. Okay, and that's where the first equivalence point is. Okay, that's your first equivalence point. Now, as this reaction continues to go, there's another proton that's going to be neutralized. That happens in the second step. Okay, so now we got a second proton that's coming off. Okay, so what happens is that this will now level off again, slowly increase, and then it's going to have a big change, drastic change, and then it will level off again. Well, this is where the second proton is coming off. Okay, so this is your second equivalence point. So you get two humps in the pH titration curve. When you add up the two equations, you see that the sodium bicarbonate cancels, leaving me with carbonic acid plus 2 sodium hydroxides plus 2 waters plus sodium carbonate. Now, if I was a triprotic, what would you expect to happen in a triprotic if I was going to do a pH versus titrant? Well, you should expect to see 3 equivalence points. Okay, 1, 2, 3 equivalence points in your titration curve. Now, we're not going to deal anything with diprotics here. Just wanted to show you a little bit about it. Now, the one thing I do want to know, if you do take this, go to another course above this, like quantitative analysis, everything that I'm teaching you how to work acid-base stuff will work as long as you do it 1 proton at a time. You would handle the first equilibrium, figure out what's left, and do the second neutralization and go on from there. As long as you do it step by step, everything I'm teaching you would still work. Such curves are used to gain insight into titration processes, and also used to determine equivalence points of things. And to do that, usually you have to have an appropriate indicator. Okay, so going back to our sodium hydroxide and HCl example, since the equivalent point's at 7, I'm going to need an indicator that's above that 7 for I know when to stop titrating. Okay, you may recall for HCl and sodium hydroxide, you tend to use phenolphthalein. That turns a pink color. Okay, well, it turns pink between 8 and 10 pH. So 1 drop past that equivalence point kicks that pH up into that region, and I see the pink color. You don't see any color change at the equivalence point because that's pH 7. It's colorless. Okay, there's no color to that. The color comes from an indicator at a certain pH range. So once we add that drop above the equivalence point, it gets into that range, and then it turns to pink color, which I'm going to show you a little bit more on the next slide. Here's an actual titration curve of a strong acid by a strong base. So we're talking about a strong acid and a strong base. And you see that the equivalence point is at 7 for this particular case. And that's only going to happen if I'm talking about a strong acid and strong base. If I'm talking about a weak component, then it's not going to be 7. You can see that the curve gradually changes, and it's got a steep change. And in the middle of that steep change is what we refer to as the equivalence point. Okay? However, when you do your experiment, you see the pink color, and then you measure that, and you call that as your endpoint. Okay, well, there's a difference between your equivalence point and your endpoint. Okay, there's something called a titration error. Your titration error which is basically we want an equivalence point, not the endpoint. So there's ways to get around that titration error. You can do a blank, okay, with no analyte in it and see how many drops it takes to turn color. You can do a back titration, meaning add more analyte into it and see how many drops it takes to go back to colorless. There's several ways you can do it to overcome that endpoint equivalence. But what you're doing is you're basically going past that equivalence point. One drop, okay, kicks it into that pink region, and we see the color change. And that's a case of my acid being the analyte and my titrant being the base. Now I can go the other way. I could say that my base is my analyte and put the acid in the burette and make that my titrant, which would mean that my reaction would be going this way, coming down. Okay, so when I reach my equivalence point, I couldn't use the same indicator because my endpoint, my equivalence point, is beyond my 8 to 10 pH. I started off at a basic pH because that was my analyte. So I'm going to need to pick another indicator that's going to have a color change beyond the equivalence point, which I could use something like bromocresol green, which has a pH range between 5 and 3 units. So once I kicked one drop past it, above one more additional drop of acid, it would kick it into that bromocresol range, and I'll see a color change, which tells me I'm at my endpoint. Okay, just to summarize some of the things I've just said, okay, first, note that the pH changes slowly until the titration approaches that equivalence point, then you got a drastic change. The equivalence point is the point in the titration when the stoichiometry amounts of reactants have been added, contrary to the endpoint, which is your observable point, and there's some difference between these two, which is your titration error, okay, between those 2 points. At the equivalence point of a strong acid and strong base, the pH of the solution is 7. Now realize it's 7 when I'm talking strong versus strong, okay, because what happens is I form a neutral salt, which in this case is sodium chloride, that does not undergo hydrolysis. So you got sodium hydroxide plus HCl. When I reach the equivalence point, all my sodium hydroxide and HCl is gone. All I have left is sodium chloride, which is going to dictate my pH, which in this case is a neutral salt. Therefore, pH will equal to 7. To detect the endpoint, we need some acid-base indicator that changes color beyond the equivalence point. Okay, basically gives you your endpoint. Okay, and that difference between the endpoint and that equivalence point is what we refer to as the titration error. You want that to be very small. You want it to be 1 drop difference between equivalence point and endpoint if possible. And there's ways to get around that error. Like I said, do a blank, do a back titration, etc. You're familiar with HCl and sodium hydroxide. We've used phenolphthalein as your indicator typically, and we know that it changes to a pink color when you get past the equivalence point, because phenolphthalein is sensitive between 8 and 10 with a pink color. So basically, once I get past that equivalence point, 1 drop of that base is enough to kick it into that pH range between 8 and 10 and get that pink color. Alright, previous example, the equivalence point was at 7, but not all neutralizations are at 7. That's one thing I want to get through to you, okay? Doing a titration of or basically if I'm just mixing an acid and a base, I can figure out what the pH is, and somewhere in that mixture is going to be a salt and water form, okay? So basically all the acid and the base are being consumed, okay? So all that's gone in a neutralization reaction. However, that base, that salt, is what's going to dictate my pH, okay? That pH is going to come from that salt. That salt can be acidic, could be neutral, could be basic. There's a misconception by students sometimes that if I have an acid and base in stoichiometry proportions that the resulting solution is neutral. That's not true. There's a salt form, could be acidic, basic, or neutral, and that's what's going to dictate the pH of the solution. Now, common sense can help you predict what the pH should be of that salt that's being formed. Let's look for instance. Strong acid and a strong base. What happens to a strong acid? Ionizes 100%. What about strong base? 100%. We're talking stoichiometry, they're the same amount, right? So we're going to be neutralizing it, right? So for every 1 drop of strong acid it breaks up, it's going to drop of hydronium, and every strong base, every drop is going to be a hydroxide. Since it's stoichiometry correctly, the H plus and your OH minus are going to cancel out. So in essence, my both strong components are canceling out. So what we have left in is no excess of hydronium or hydroxide. So we end up making a neutral salt. So this is the only true neutralization where the pH is 7 at the equivalence point. This is the only true neutralization with equivalence point being at 7. Let's look at a weak acid and a strong base. Strong base, every drop gives you hydroxide. Weak acid, every drop gives you less than 5% hydronium. So I have an excess of strength coming from that strong base. Well, common sense will tell me then what should be left over in my solution. Some basicity. So therefore I would form a basic salt. Which means my original acid and base have neutralized. They're gone. Okay, and the only thing left is that salt, which has basic properties, and I expect a basic pH for my equivalence point. pH will be less than 7 because it's coming from that basic salt being formed as a product. What about a strong acid and a weak base? Well, once again, the weak one does less than 5% hydroxide. Acid, strong acid, every drop, I'll get a drop of hydronium. So then I have an excess of strength coming from my strong acid. So what do we expect to form then? Acidic salt. Once again, acid and base components are canceled. However, I'm making acidic salt, so I have acidic pH. So then my equivalence point will be some acidic pH, be less than 7. Okay, so we expect the equivalence point to be less than 7. We expect it to be greater than 7 for our basic salt. Now, when working with acid-base titration problems or mixtures, which is what we're going to do, all we're going to do is mixtures, okay? We're going to basically do our neutralization and then examine the components to see how they affect the pH. Is it a strong acid, weak acid, salt, etc., and go on from there, which is similar to what we did in the past, okay? But we've got to get there first by doing our neutralization first. Now, you can do a calculation for each spot on a graph. So if I wanted to, I can derive and get every point on a curve and derive a whole curve by calculating. Okay, we can do that. Or what we're going to do is we're going to pick one particular point and say, I got this much volume of this molarity of acid and this much volume molarity of base. What's the pH? Okay. Now, how we're going to do that is we're going to follow these steps. Okay, these 4 steps. These are the same steps we talked about when we did that change in pH for the buffer. Remember, I told you we weren't going to make you calculate change in pH for the buffer, but it is the steps that we're going to follow when we get to neutralization. So it'll be just like that problem we did earlier. First step, you're going to calculate the millimoles initially you have of every component. Okay. Second, you're going to write the neutralization reaction and find the millimoles of components after that neutralization. What's left to affect the pH? Third, you're going to find the new concentration of the species that affect the pH. Only those things that are affecting pH. I'm not going to do everything. Only the things I know are going to affect it. And last, you do the hydrolysis of the main species that affect pH. This is like we've been doing, okay? So we already have done step 4 and all the problems previous to now, okay? What we're going to have to do is do 1 through 3 before we do step 4, okay? When we're dealing with a neutralization. So how we're going to do this is teach you this through doing several problems. Let's look at this problem. Calculate the pH of a solution in which 50 milliliters of 1 molarity sodium hydroxide is added to 50 milliliters of 1 molarity of HCl. So the way our process goes, we say, is this a single solute or reaction? The answer is it's a reaction. Since it's a reaction, our next question is it a neutralization or is it a buffer? And the answer is, well, it's just a strong acid, strong base. That's just a neutralization. So how do we handle neutralization? Is we go through those 4 steps. Okay. Now we got an idea where this is going to end up since we're looking at a neutralization and we got sodium hydroxide and HCl, which are 1-to-1 mole ratios when I balance the equation, and I got 50 mils of 1 molarity in both. Okay. Well, where are we in this reaction? Oh, we're at the equivalence point. Since this is a strong acid and a strong base, we know that the answer already is going to be what? pH is equal to 7. Now, is it pH to 7 always anytime I got an acid and base at the equivalence point? The answer is no. Only because I have a strong base and a strong acid that I know that it's going to be there. But we're going to go ahead and do the calculation before we can see how we arrived at that decision, the process. That way I want you to do the process every time, and that's going to dictate where you go in the problem. So first step, millimoles. Okay, I want to calculate the millimoles of my components. Now, how do we do millimoles? Millimoles is just going to be basically your molarity times your volume. Okay, and we're not going to change the units. We're going to leave the volume in milliliters. That way I can get millimoles. Okay, so in this case, I got my HCl, I got 50 milliliters times 1 mole per liter. Notice that my liters cancel, but my milli did not cancel. That's just a prefix, so that's going over to my moles, which leaves me millimoles, which in this case is 50 millimoles. Sodium hydroxide, same calculation, 50 milliliters times 1 molarity, which is 50 millimoles. Step 2, we said, is neutralization. Okay, so I got to write the neutralization reaction. It's important that you can write a reaction. And this is all acid-base stuff. That means the proton of the acid is going to come over and displace the cation, and that's going to come over. Okay, which means I get sodium chloride in water. Then we're going to write a table. It's not an ice table. It's a change in millimole table. Okay, so we're just looking at millimoles. Okay, so we're going to write our initial millimoles, which we know is 50 for HCl and 50 for sodium hydroxide. How much do I have initially of sodium chloride? Well, that's nowhere in the problem. That's going to be formed as a product from this reaction, so I have 0. Now I need to do a change in millimoles. Okay, how much is it changing? Well, this is all based on limiting reagent, and everything we do with acid-base is 1 to 1. We do 1 proton at a time. So basically, it's going to end up being the smaller number of millimoles. It's going to be my change. In this case, it's the same number, so they're both going to be 50. But the one thing to realize is on the reactant side, it's being consumed, and on the product side, it's being produced. So my change will be minus 50 on my reactant side and plus 50 on my product side. Do the math. So my millimoles at neutralization, which is the stuff that can be affecting my pH, are 0 for HCl, 0 for sodium hydroxide, and 50 for sodium chloride. Since I got 0 and 0 at my equivalence point after neutralization, I got 0 and 0 after the neutralization, I am at my equivalence point, which we know. We already discussed that. However, that doesn't tell me what the pH is unless I have a strong species, which is the case in this particular problem. But we'll continue on with our thought process. Next step is the new concentrations of the species affecting pH. Well, naturally, HCl and sodium hydroxide cannot affect it because I have none of it. So the only thing that can affect this is the sodium chloride. So let's look at sodium chloride. What kind of species is that? Well, it's a salt, a soluble salt. What kind of acidity, though? Is it an acid, base, or a neutral salt? It's a neutral salt. Well, how does a neutral salt affect the pH? It's neutral. It's 7. So all I have is water and sodium chloride, so those are both 7, so they're not affecting it. So in essence, the pH then of this reaction at equivalence point will end up being 7. Okay, so the answer is pH is 7, but realize this is a strong acid and a strong base. Okay, if it was a weak acid and a strong species of some sort, it will not be 7. Okay, keep that in mind as we'll see in later examples. Let's look at this reaction now. pH, we're going to calculate the pH of a solution in which 49.99 milliliters of 1 molarity sodium hydroxide is added to 50 milliliters of 1 molarity of HCl. Okay, so is it a single solute or is it a reaction? It's a reaction. Is it a neutralization or is it a buffer? Neutralization. So the first step is figuring out your millimoles. Now let's look at this a little closer before we do it. I got 49.99 of 1 molarity of sodium hydroxide and 50 milliliters of 1 molarity of HCl. So in this case, since it's 1 to 1, I have an excess of acid. Not much. Okay, we only got 0.01 milliliters from the equivalence point. We're only 0.01 milliliters away from the equivalence point. Okay, so we very little. We got less than a drop from a burette. Okay, a drop of a burette is around 0.05 milliliters. We're at 0.01 milliliters, so we just about it. The interesting thing we're going to find is let's see how that pH differs from that equivalence point, which we just calculated was 7. Let's see what it is, and I'm only 0.01 milliliters away. Since I have an excess of acid, I expect the pH to be less than 7, okay, because I have an excess of acid. Let's look at my millimoles of each component. Got my 49.99 times 1, which is 49.99 millimoles of sodium hydroxide. 50 times 1, which is 50 millimoles of HCl. Got to write my neutralization reaction. HCl plus sodium hydroxide. The hydrogen comes over, forms my sodium, which gives me sodium chloride. Then I do my millimole table, which is my 50 and 49.9 for my sodium hydroxide. And 0 for my sodium chloride. Okay, because I have none to start with. It's only going to come from my reaction. So now I got to do my change in millimoles. Okay, so I'm going to do the smaller number since it's a 1-to-1 mole ratio. That's going to be my limiting reagent. So I got my 49.9. Once again, I'm going to have minuses on my reactant side and pluses on my product side, which gets me after neutralization. I have 0.01 millimoles of HCl and 0 millimoles of sodium hydroxide and 49.99 millimoles of sodium chloride. Next step, new concentrations of the species affecting pH. What is HCl? It's a strong acid. Can that affect the pH of the solution? Yes, so that's something I got to worry about. I have 0 sodium hydroxide, so obviously that can't affect anything. What about 4999 millimoles of sodium chloride? What is that? It's a soluble salt. It's a neutral salt. Can that affect pH? No, so I'm not going to worry about that. So the only thing that can affect pH is my HCl. So I'm just going to determine the new concentration of that species only. So how do I do that? I figure out my millimoles remaining, which we know is 0.01. Okay, that's coming from right here. And put that over my total volume, okay, which was 50 milliliters of acid and 49.99 milliliters of my base, which gets me a molarity of 1 times 10 to the negative 4th molarity. Now, what we are right now is at a point where we're just talking about a strong acid here. So it's just like I rewrote the problem and said I got 1 times 10 to the negative 4th molarity of HCl. What is the pH? This is what we did back a long time ago, the first time we did a calculation of an acid, okay, the strong acid. It's like I've got a strong acid at a certain concentration, and we go on with the hydrolysis just like before. We had to do these first 3 steps to get to that point. So next step is hydrolysis. So hydrolysis of strong acid, what do? We break up that HCl, okay, into hydronium and Cl minus. Since it's just strong, it breaks up 100%, which means I got 1 times 10 to the negative 4th molarity and 1 times 10 to the negative 4th molarity. And then I need my pH. pH then is equal to the negative log of my hydronium, which is the negative log of 1 times 10 to the negative 4th, which is equal to a pH of 4. Notice that we're only 0.01 milliliters from the equivalence point. And the pH went from 7 to 4. Okay, that's a large change by 0.01 milliliters. Okay, so when we get close to the equivalence point, the pH changed drastically. Okay, it went down by 3 units by only 0.01. As I said, that's equivalent to about 1/5 of a drop on the burette. And this is where, when we do our titration, we have that indicator. We pick an indicator that when we do that 0.01 milliliter difference, that it's going to change dramatically, and that pH is going to kick into that pH range to see the color change to tell us that we've hit the end point, therefore we need to stop titrating. Let's look at this one. Calculate the pH of a solution in which 5.01 milliliters of 1 molarity sodium hydroxide is added to 50 milliliters of 1 molarity HCl. Single solute or reaction? Reaction. Neutralization or buffer? Neutralization. Let's look at it before we move on to the steps. We have what? A slight excess of base now. So where do we expect the pH to be? We expect it to be above 7. Okay. Now, can we make a guess of what it should be if we understand the concept that we're dealing with? Remember, we just did the problem just like this, and we were 0.01 milliliters below the equivalence point. Now we're 0.01 milliliters above the equivalence point. If the pH was 4 last time, being 0.01 below, where do we expect the pH to be now since we're 0.01 milliliters above? Exactly, it should be around 10. Let's do the calculation. First step, calculate the initial millimoles of each component. So you got your 50 times 1, which is 50 millimoles of HCl. Your 50.01 times 1, which is 50.01 millimoles of sodium hydroxide. Next step, neutralization. Write the reaction. Gives me sodium chloride as a product. Then we write our millimole table. 50, 50.01, no sodium chloride. Got to do my change, so we take the smaller number, which is 50. So I got minus 50 on my reactant side and plus 50 on my product side, which means I have 0 HCl at neutralization. I have 0.01 sodium hydroxide, and I have 50 millimoles of sodium chloride. Next step, new concentrations of species affecting pH. Okay, well, HCl has 0, so that's not affecting it. What about sodium hydroxide? What is that? That's a strong base. Does that affect the pH? Yes, I got to worry about it. Got 50 millimoles of sodium chloride. What is that? That's a neutral salt. Will that affect pH? No, so I don't have to worry about it. So I only have to worry about the strong base. This is where all my pH is coming from, so I will calculate the new concentration of my sodium hydroxide only. So sodium hydroxide after my neutralization be my millimoles, which we said is, which would be my 0.01 millimoles over my total volume, which is 50 plus 50.01, which is 1 times 10 to the negative fourth molarity. Now this is just like I had a 1 times 10 to the negative fourth molarity solution of sodium hydroxide and want to see the pH of it. So it's just a hydrolysis, the step that we were done a long time ago, and a long time ago in our lectures. So then I'll do my hydrolysis. Okay, which means I'll write my sodium hydroxide equation, which breaks up into sodium ions and hydroxide ions. Concentration, 1 times 10 to the negative fourth sodium, 1 times 10 to the negative fourth molarity of hydroxide. Get the pH. I'll do it the way where I told you I'd do it. pH is equal to 14 plus the log of the concentration of hydroxide, which means 14 plus the log of 1 times 10 to the negative fourth, which is equal to 10, which is what we expected. Once again, one drop past the equivalence point kicked it up into that range of 10 pH. Now notice normally we do it, we got HCl as our analyte and sodium hydroxide as our base in the burette. We usually have phenolphthalein as our indicator, and typically phenolphthalein is a pink color between 8 and 10 or so. So when I add that one drop, it kicks it past that equivalence point into the endpoint of 10 pH units, and it turns pink. Okay, and that's why we see that pink color. That one drop is enough to kick it into that color range that we can say, oh, we're at the end point, we need to stop. Now, as I said before, there's a titration error there, and there's ways to get around that when you're doing your actual calculations. Now, you might notice on our calculations on our pH versus our volume, milliliters of titrant, in this case we're doing sodium hydroxide as our titrant, down below the equivalence point, okay, in this area we ended up always having an excess of acid, and in this range we always had, we're going to end up with an excess of base. Okay, now if I did it the other way where I had sodium hydroxide as my analyte and HCl was in my burette and I was adding it, well then, you know, at the top before the equivalence point I'll have excess base, and below it I'll have excess acid. Homework 38 deals with, okay, homework 38 deals with titrations or mixtures dealing with strong acids and strong bases. Now, as I always caution you, 38 only has strong. Don't get used to that. You want to always be looking for things because on the test you have them all mixed up. You're going to have weak strong and strong. Okay, so even though the homework assignment is all strong, you want to think about it and ask about the questions and go through the procedure.